Alright, this is example E3.2. It corresponds to problem 3.80 in the text. And yeah, here's the exercise. You can see that there's a structure that's supposed to represent a model of a retractable tool holder. So the tool is connected here at point D. And what happens is when the tool is used, the worker will grasp it and apply a downward force, which lowers it. And then when you're no longer using it, you let go of it, and the spring causes the tool to retract up and out of the way. And they tell you that the spring stiffness is 2 pounds per inch, and that you can assume that the worker is pulling straight down on the tool. Further, the unstretched length of the spring is 30 inches, and when there is no force being applied, you have a triangle with alpha and theta both equal to 60 degrees. So the question asks, what is the value of theta? So how much does this bar have to rotate if I'm pulling down with a force of W equals 15 pounds? So I'll let you work on that, and then come back and we'll go through the solution together. Okay, so this is a problem in the book that has a little label indicating that it's very difficult to solve it by hand. And the reason that it is because as you write down the equations, you end up with this large coupled set of equations that have to be solved simultaneously. Of course, is at least tedious to do by hand. It's much easier to do using a computer program, so that's what we're going to do. And the way that I'm going to tackle this problem is I am going to start by assuming that I know a value of theta. So I'll assume a value of theta, and what that will allow me to do is first of all specify the geometry. So I'll know the positions of point A here, and then of course that lets me calculate the length of the spring, which means I can figure out the spring force, and it also lets me figure out the direction of the spring force and the direction of the force in the bar. So then it's easy to do a free body diagram on point A, which will then allow me to calculate the value of W. Right? And once I have that working, it's possible for me to just adjust theta until I get the value of W that they're asking for, or better yet, just let ease do that for me. So that's a pretty logical way to approach this problem, and that's what we'll do. So I'm going to go ahead and enter the inputs to the problem. So the inputs to this problem are that theta is, for us, we're going to assume it's given, so 70 degrees. And again, this is going to be an assumed value of the angle theta. I know the free length, the unstretched spring length, so L0 is 30 inches. And I know the spring stiffness is 2 pounds per inch. And since I'm dealing with angles here, I better set the unit system to be degrees. Alright, so what's next? What's next is, because I know theta, I can figure out the position of each of these points A, B, and C. So I'm going to let B be 0, 0, and I'll figure out A and C relative to B. So these points are defined as vectors. So dollar vector 2D, A, B, and C. B is 0, 0, so that's easy. Let's see, C I know is 30 degrees up from B, so C is 0, 30. These are in inches. And then A is, let's see, A depends on theta, right? And it's 30 inches from B, and it's rotated relative to the x-axis 90 degrees minus theta. So I can use vector assigned polar to get point A. And I can solve at this point and make sure that these points kind of look right, which they do. Once I have all 3 points, I can define two position vectors, RAC and RAB, that are along the length of the spring and then along the direction of the bar. So I'll go ahead and do that. RAB is B minus A, RAC is C minus A. So those are vectors. Now I have to start thinking about a free body diagram on point A. So point A has three forces on it, as shown here. There's the spring force, there's the force from the bar, and then there's this vertical force downwards from the worker. So let's see, the spring force, I think I can calculate. We are elongating the spring, so it's going to be pulling on point A as I've drawn it here. And the magnitude of that spring force is going to be the spring constant K multiplied by the length of the position vector RAC minus the free length, right? That's how much I have elongated the spring. So I'm going to calculate here the magnitude, and then I also know the direction. So the spring force vector is the magnitude of the spring force, and then the direction defined by RAC, which is just the position vector RAC divided by its magnitude. Alright, so we have two other forces I have to think about, right? I have the force W, and I know its direction but not its magnitude, so I'll go ahead and define a vector W as being let's see, having no component in the x direction because it's vertical, and then minus the magnitude of W in the y direction. And then I have one more force, which is force from the bar. I know its direction, but not its magnitude. So the force from the bar, FAB, has some magnitude, mag FAB, and then it's in the direction defined by the position vector RAB. So I'd multiply that by that vector divided by its magnitude. And at this point, I've added two unknowns, but I don't have enough equations to solve. If I tried to solve, I wouldn't be able to. So the last piece of information is the equilibrium equation for this problem, which is in two dimensions, and it just says that these vectors have to sum to the zero vector. So W plus F spring plus FAB, those vectors have to equal the zero vector. So that's easy to enter. I'll enter that in ease. And at this point, hopefully, if I haven't made a mistake, I have enough equations and enough unknowns that I can solve. And you can see that the solution tells me that the magnitude of W is like 7.7 pounds, right? So when I rotate 70 degrees, I get a magnitude of W that's 7.7 pounds required for that rotation. Of course, that's not what the question asked. The question asked, how much do you have to rotate in order to get a magnitude of W that's 15 pounds? And so that's pretty easy to do here, right? One way to do it is I can just go up here and change the value of theta manually and each time solve and see when do I get close to W. And that's fine. What's probably easier is to ask ease to do that calculation for you, right? So now you're asking ease to solve a relatively large set of equations simultaneously, and it's going to iteratively try to do that. One thing that you can do to make its life easier is to start that iteration process from a good starting point. And the way you do that is you select update guesses from the calculate menu, and what that does is it basically sets the starting point for every variable to the current solution, which is a really good place to start versus their default values. So once I've done that, then I'm going to go ahead and comment out this value of theta, and instead I'm going to set that the magnitude of W needs to be 15 pounds. And it will solve now and tell me that if you want 15 pounds, theta has to be equal to 83.62 degrees. So again, once we have a solution, because we did it in the computer, it's easy to do a lot of kind of interesting studies with it. So one thing I can do with this solution is just do a vector plot that shows the free body diagram just to see how that looks. So if I want to do that, I'm basically going to plot the three vectors representing the three forces on point A. So I'd go to plots, new plot window, vector plot, and we can start them all at the origin, and I want to put FAB, so I'll plot that, F spring, and W. So those are the three plots, and then I'm done, and you can see that's the free body diagram. I have the spring force pulling this way, I have the workers force pulling down, and then the bar force is actually pushing, and so opposing the spring force in some way. So that's kind of interesting. If I want to, I could also look at the geometry. So the geometry is basically specified by these two position vectors, right? So I would plot those two position vectors. So vector plot RAB and RAC. And that's what that plot looks like. So you can see that this point has actually been pulled down. Actually, what's really kind of cool is if I click on this, I can go down here and do automatic update. And so this is what the position looks like after I have pulled on the retractable tool holder with 15 pounds. When I reduce the amount of, so let's make this just 1 pound, and we'll solve. And because I have auto update checked, you can see I'm gonna have to extend my scale here. So let's go down to minus, I don't know, minus 30. You can see that now it goes back to being much more of a sort of 60-60-60 triangle, right? So that's kind of cool to see how the geometry changes. The last thing I think I might want to do is look at as a function of that force, what is the angle, or what is the deformation of point A, right? Those are the kinds of things that I could look at. So now I don't want to specify either the magnitude of W or theta. Instead, I want to actually vary either theta or the magnitude of W and look at how one thing changes and how the other thing changes. So let's make a new parametric table. 10 runs seems probably good enough. In here, I want to put for sure theta, the magnitude of W, and what else might I want to put? Maybe I want to put the position of A. So this would be A sub Y, I think, right? So how much does point A change its position vertically as I pull on it? And I can change theta from, I don't know, let's change it from 65 degrees to 90 degrees. And hit OK. And we will run this table. So calculate, solve table. And you can see that as you rotate theta down, the magnitude of W goes up and the position of A sub Y goes actually down, right? And I can plot these. So I'm not sure what the best way to plot this is, but let's put theta like that. So yeah, there's my magnitude as a function of theta. And I could also do, let's do theta and AY. So there's AY as a function of theta. So if I wanted to design one of these things, right, I might have some specification that 15 pounds should move my tool 10 inches. I could now do things like change the spring constant, K, or change the free spring length, L, or the geometry, these 30 inches, in order to hit some kind of design considerations. And that's where you're really going from kind of a textbook problem into the real world, where you actually have to design a mechanism to do a certain job.